recording.
Alright, morning everyone. So to pick up where we left off, we were talking about functions, right? And we motivated learning about some special kinds of functions by asking when we could turn a function around the opposite way and still have a valid function. And right, since a function has to have exactly one output for each input, or exactly one arrow coming out of each thing. That means in order to be able to turn it around, we have to have exactly one arrow going into each thing on the other side. And so we were kind of exploring two different types of functions that kind of deal with one of those problems we had. So the first thing we talked about, right, is that a function could be injective, which means essentially we can't have two different inputs that go to the same output. Right? Or put it a different way, any two different inputs always go to different outputs. So I think we had done some examples and we had convinced ourselves that double is, let's see, double is injective, right? G is also injective. H is not injective. Q, I guess, we had convinced ourselves also is injective, although we can think about that one a little bit. Okay. So I guess the first thing I want to do actually is just really quick, let's write down, I'll switch over and write. So I'm going to write down like an actual proof that double is injective. So we can kind of wave our hands and be like, oh yeah, like any two different inputs will do different outputs, but how would we actually write a convincing proof of that? So I will show you how. It's not hard, but so we have double and equals 2n. So claims that double is injective, right? And well, what does injective mean? If we write it out formally, this means, and you wouldn't have to write this, but again, this is going to help us think about how to structure our proof. If we think about formally what this says, for all, well, I should say double is a function from natural numbers to natural numbers. So for all n natural number, for all n, oh, sorry, yes, all n is a natural number. I'm just going to call it d because I'm running out of space. So if dn equals dn, then n equals n. Okay? That's one way of writing the definition of the injective that we wrote down last time. Okay? So we can just look at this and it's going to pretty much tell us how to structure our proof. Okay, so proof. Well, starting out, I have some for alls, right? That's the big thing at the top, is that I have some for alls. And so how do I prove a for all? Well, the only way we know right now to prove a for all is just to say, suppose I have some arbitrary natural numbers, and I need to prove, that no matter what those numbers are, that this will work. So I just say let n and m be arbitrary natural numbers. so now I have to prove this part. So this is an implication. It's an if. So how do I prove an implication? Well, again, we have a few choices, but the simplest way to try would be to just say, suppose the part on the left, and then we have to prove the part on the right. So I'll just say, and suppose that double m equals double n. And then just to remind ourselves, or to remind the reader, right, I can just say, we must show, right, we suppose this, and now we have to show this. We must show that n, I guess I got m and n backwards, didn't I? Not that it really matters, I mean, show that n equals n. Okay, well, if double n equals double m, what does that mean? We know what the definition of double is. So we could say, you know, double n equals double m. That implies, by the definition of double, that 2n equals 2m. Right? Well, okay, now I just divide by 2. If I divide both sides of this by 2, this implies n equals m. Oh, that's what I was trying to show. So, is this overkill for this simple example? Probably. But, this is, you know, just thinking about things intuitively and kind of being like, well, it makes sense that blah, 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 that'll get you a certain, you know, that'll get you so far, and then you'll run into things where your brain, your puny human brain can't hold, you know, all the stuff in it at once, and you need to be able to write things down more formally, keep track of where you are. So that's what I wanted to show. That. All right. Any questions about this? And when I say your puny human brain, I include my brain in that too. I'm not saying like, oh, you all have puny brain. Humans have puny brain. We can only hold like 7 things in our head at once, and then things start falling out. So that's a big part of why stuff like this is helpful. If you can write stuff down in a careful way, right, you're using the paper as an extension of your brain. Right? It's specifically as an extension of your memory, because your memory cannot hold very many things at once. Right? Do you all know this? Like, you can do experiments to, like, you know, ask people to remember certain words or whatever, and like, it's about 7 is the number of things you can kind of hold in your working memory at once, and more than that, you literally cannot remember more things than that. You might think you can remember more than that, but either you're mistaken, or what you're actually doing is like grouping multiple things together into one thing, and then you're just remembering that. But then you can kind of like, you know, if I can like have these 5 things, and I can kind of categorize them all into one thing, and I can just remember that one thing, now, I only remember one thing. But, and that's, right, that's abstraction, right? That's why, that's how we're able to do more complex things, if we can start packaging things up into single concepts that we can hold in our memory at once. Let's just do more stuff. Or we can use paper. All right. Cool. So, injective functions, right, were functions that don't have this problem of multiple things going to the same thing. So the other problem we could have, remember, is if there was something on the right side. I'll draw a picture. Right, something like this, where we had a picture of something like this before. Where, I mean, this is a perfectly good function, but we're not going to be able to flip it around backwards because this thing doesn't have, anything going into it, and so it wouldn't have anything coming out of it if we put the ref. So we can also, of course, define a special kind of function that doesn't have this problem. So this is called an onto, or the fancy math word is I'll say a function f from A to B is onto, or a surjection, or the adjective form is surjective, if what? Basically every B has an A that goes to it. So how do we want to say this? We could say it intuitively as every element of B is covered. I.e., every element of B occurs as an output of F. Okay. Formally, we can say it like this. For all B, so for every B, there exists at least one A such that what? Such that F of A is equal to B. Okay? So no matter what B I pick over here, I'm going to be able to find some A that the function, when I apply the function to that A, I get that B. Okay. There could be more than one A, that's okay. I just need at least one. Okay, and what is the negation of, right, so in other words, if I wanted to show that something was not onto, what would I have to show? Well, again, we can just apply not to this and use our various De Morgan style laws to simplify it. So if I apply not, what do I get? I get, well, this turns into an exists, and then I have not this, which turns this into a for all, and then I just have not FA equals B, which I could also write FA is not equal to B. Okay, and what is this saying? This says there is some B such that for every A, right, no matter what A you pick, F does not, like if you put A into F, you don't get B. In other words, there is some B. This B is not the output of F for any A. That intuitively, that makes sense. That's what this picture shows, right? This B is, would be something like this here. Okay. Questions? Okay, I'm going to give one more definition, and then we're going to go do a bunch of examples. So, definition. This is kind of the original motivation. A function which is both one-to-one and onto, right? If it has both those properties, that means we can flip it around, and that the flipped around version will also be a function. Okay, so this is called invertible, or we could call it, fancy math word is bijective, or we could say it is a bijection. Okay, in this case we write, I should say a function f from a to b. We write f inverse from b to a, say for the inverse of f. That is, right, that's like f flipped around. So the function defined by, well, f inverse of b equals a if and only if f of a equals b, right? So they're just exactly opposite. If f sends a to b, then f inverse sends b back to a. F inverse undoes whatever f did. So the picture is something like this. Here's A, here's B. Right, it's F is 1 to 1, so I can never have two arrows going to the same dot over here. It's also onto, so I have to have an arrow going to every dot on the right side. So maybe it looks like this, right? But I can kind of turn it around and say, like, this direction is F, and this direction going backwards is F inverse. Kind of matches up the things 1 to 1. And I think someone said, or I think maybe it was Garrett said last time, like, well, they have to have the same size. And you can see intuitively that's true, right? A and B have to have the same size for this to work. Right? Like if B is bigger, then there would necessarily be something that gets left out. Right? There wouldn't be enough things over here to hit everything over here. And if B was smaller, then we would get stuck having to have two arrows go to the same element. There's not enough places for them to go, right? This only works if you have exactly the same number. Be careful. Actually, I'm going to write this in red. There is a slightly unfortunate kind of notation clash here, so careful. This notation f minus 1 means the inverse of f. It is not the same as 1 over f. Okay, usually you might be used to seeing a negative 1 exponent mean 1 over whatever, right? But when we're talking about the inverse of a function, it doesn't mean that. Right? 1 over a function is not the same as the inverse. I mean, except for like maybe a very specific one. It's unfortunate in one way. I mean, it's actually the case that if you generalize enough, if you look at it from an abstract point of view, like 1 over f is a kind of inverse also, right? And it kind of makes sense that the notations are the same because, you know, from a sufficiently general point of view, they're kind of the same thing but in different contexts. But that's still confusing. So in this class, I will never use the minus 1 exponent to mean 1 over something, because we're never going to need to do that. We'll always use it to talk about function inverses. And usually it's pretty clear from the context of whatever you're doing. If you're talking about functions and you have, you know, f minus 1, you're like, okay, it's talking about the inverse of f. If you're talking about, like, you know, polynomials or something, or you have like x squared plus, you know, x minus x to the minus 1. Like, okay, x is representing like a number, it's not a function, so that can't be an inverse. So usually it's pretty clear. Okay? more thing, let me see page, to prove that a function is a bijection, aka invertible. Well, according to the definition, one thing we can do is we can just prove separately. We can prove it is one-to-one, and prove that it's onto. Right? The definition literally says it's invertible if it's one-to-one and onto. So how to prove an and? You just prove both things. It turns out there's other ways you can do this, and you might see, like, if you read other books or find other videos about bijections, internet, whatever, there's other ways that you can prove it. So, for example, we can also basically find another function g and show they are inverse. And to show their two functions are inverse, we have to do two things. We have to show that f of g of x equals x. So this says, look, well, for all x, I should say. For all x. F of g of x equals x, and g of f of x equals x. So this says, like, if you start with something and you go, you see where, you do f and then you do g, you get back to where you started. And the other way around. If you start over here, you do g and then you do f, you get back to where you started. If those two things are always true, then those functions are inverse. And it turns out that having an inverse implies that it's a bijection. You just have to be careful though, because if you only do one of these two things, you haven't finished the proof. And it turns out that you can have one of these but not the other. That is possible. All right. Anyway, probably do some examples of that. But right now, what I'm going to do, just do a bunch of examples of functions and think about whether they're one-to-one or onto bijections. Okay. So we saw, I guess I don't want to, okay. So this is injective. This one is also injective. Right, this one is not injective. Okay, so I'm going to take this out. That's not true, right? This is also injective. Okay. So let's think about the functions that we have here and think about which ones of them are onto. And then maybe we'll write some other functions and think about them too, but we'll start with the ones we have. So what about double? What do y'all think? Is that onto or not? Remember what onto means, right? Every element of the codomain of the output has to be covered, right? There has to be some way to get it as the output of the function somehow. So is double, how many people think double is onto? How many people think it is not? Okay, so everybody thought it was, stand up and go over there, and then we're going to have a fight. No. Anyone want to argue for one or the other? Why you think either it is or isn't? So so now that you know that there were multiple people who thought both of those things, you don't have to feel like you're the stupid one that everyone else knows, right? So,
I think Garrett said this yesterday, but like for the outputs, you're never going to get any odd numbers.
okay, so you're saying you're never going to get any odd numbers as output? Do you all agree with that? So does that mean it is or isn't onto?
It is not.
It is not, okay. What do you think? Yeah, right? Onto means, so the codomain of this function is the natural numbers. So for this to be onto, it means I have to be able to get every possible natural number out of this function. But Matthew is arguing, no, that's not true. We can't get every possible natural number out. We can only get even numbers out. We can never get odd numbers out. So it's not onto. Okay, and right, we could try writing down a property, and hopefully Disco will show us that it fails, right? So I'm going to say for all E n there exists a n such that double A equals B. Right? That's what it would mean for this to be onto. For every element of the output, there exists some input. And if I reload this, right? It says, so it's a little interesting actually. Disco isn't quite sure, right? It says, well, I didn't find an example. It says here, so here's B equals 1 is something that I found. It seems like maybe this makes it false. But, like, it can't, Disco doesn't know for sure that there's no A that works, right? Because it's not really smart enough to, like, solve the equation. It says, look, I tried B being 1. And then I tried to see if there's an A such that double of A equals 1. And I tried 50 examples, and none of them worked, so maybe there is one, right? But that's good, it's like, well, at least it gives us a place to start. And say, oh, B equals 1, okay. Is it possible to get 1 out of this function? No, actually, I can reason about it, and I can see that that's not possible. So it's in fact, so Disco is actually right. But if we had made the function like, oh, in general, double n is 2n, but like double of 5,289 is equal to 1. Right? Disco wouldn't find that because it probably wouldn't randomly choose that number. So, anyway. But not surjective. So injective means 1 to 1, and surjective is 1 to 1. Okay, how about G? Is G onto? No? I see some shaking heads. So, okay, if you think it's not onto, give me an example of a natural number that we can't get as output. 1, 0, 94, I mean, there's a lot, right? Yeah, so this is like very not that there's any such thing as being like only a little bit not onto or very not onto, but if there was, this one is very not onto. By the way, is it possible, so this function here is from natural numbers to natural numbers, and it's not onto. Is it possible to make a function from the natural numbers to the natural numbers that is onto? Can you think of a function from natural numbers to natural numbers that is in fact onto?
You restrict the codomain to be the subset natural numbers that are even. That way.
Oh, okay, yes. That's one thing we could do. If you wanted to like fix this function and make it onto, you could say, well, I don't want n as my input. I want just. I don't think that would work. You could yeah, the codomain. You could say, no, I'm not going to open any natural number. I'm only opening even numbers, and then that would be onto. That's not what I'm asking though. I don't want to fix this function. I just want to say, I want a function with the same type that takes a natural number and gives a natural number. Can we come up with a function that has that same type, a different function that is actually onto? Matthew?
N equals N.
Yeah, so if I just, like the identity function, it just returns the same thing that you input, right? Then if I want to get, x as output, I can just put x as the input and I'll get that. So, and there's other ones, there's lots, right? Yeah, sure.
It's just do something like n2 and plus 2, right?
And, okay, yeah, good. Let's try that. So, we'll call it f. Well, so first I'll say this ID, right? ID n. This is injective, or it's 1-to-1 and onto. So Garrett was saying, what about f of n equals n plus 2? What do y'all think? Is that onto?
Are natural numbers always positive?
Yeah, what's natural numbers? What's the definition of natural numbers? Yeah, it's like 0, 1, 2, 3, etc. It does not include negative numbers. So Olivia's shaking her head now. Why are you shaking your head?
Because you're not going to get 0, 1, or 2.
Right. 2 you can get,
Yeah.
but not 0 or 1. Yeah. So this is actually a really interesting point. So this function f is not onto, right? We can't get 0 or 1 as output because it's defined on the natural numbers, right? However, this function, we'll call it f prime. If I say, oh, this function, it has the same definition, f of n equals n plus 2, right? But this function is defined as going from the set of all integers to the set of integers. Is this function onto? This one is onto. Because I have all the negatives and positives, right? Any number that I want as output, I can just input 2 less than that, right? Which kind of always exists because, even if I want 1 as output, I can put negative 1 as input. But in this case, that doesn't work because if I want 1 as output, there's no natural number that's 2 less than 1. What this function is. Okay. So that just shows that the type of a function, right, kind of what you specify as the kind of the set of input and the set of output, that makes a big difference as to whether we would consider it 1-to-1 or onto or whatever. Even though you can't just look at the definition, you also have to know this information about the input, the domain encoded. Okay. This function, what about this one? So this one we also said was not onto. Can I come up with a different function from bool to n that is onto?
Does it also have to be injective or just
No.
For onto, if it's true, you can return all natural numbers, and if it's false, you can return all negative integers.
Well, so this, I think I see what you're trying to do, but this, remember that a function can only give exactly one output for each input, right? And this says it outputs a natural number. I can't output like a set of natural numbers. I have to output one natural number, and I only get to pick one for each possible input. Matthew?
You wouldn't be able to because there's only 2 possible inputs. So it could be a function, it could each only have 1 output, so you can only get 2 natural numbers.
Right. Yeah, so Matthew's saying, like, I have to, there's only 2 possible inputs. for each input, I get to pick one natural number to be the output. So that, I mean, that's necessarily going to leave a lot out. There's nothing I can do about that, right? In some sense, there's so many more natural numbers than Booleans that I can't possibly cover everything. So, in this case, right, this one just kind of happened to not be onto, but we could make something with the same type that is onto. This one, like, it doesn't really matter. You don't even have to look at the definition. You're like, there's no way. That can't be onto because you can't cover everything. So again, we see that the sizes of the input and output sets has a strong relationship with whether things can be one-to-one or onto. Okay. How about this function h? Is this one onto? How many people vote yes? Okay, and a bunch, anyone think no? Okay, so it seems like, anyone want to explain why you think it is onto?
Both true and false are covered.
Right, yeah. The output type is Boolean. There's only two possible Boolean values, and we can just look and see, like, look, I can get both of those as output from something, so covered everything. If you want to be, really specific, you can pick some particular numbers and say, well, if I input 3, then I get true, and if I output 4, I'll get false. So there's some specific examples that show that, yes, I can get out every possible thing. But it is onto. Okay. More examples. Okay, wait, did we have one that was both? I'm going to change the name of this to like. So I claim this function k, I claim it's also one-to-one. So if I have any two different integers, and I add 2 to both of them, I'm still going to have different, if I started with different things and I add 2 to both, I still have different things. Right? So this one is also invertible. So that means this function k is invertible. And one-to-one. Okay, so what would be the inverse function of k? So I'll call this k in. What's the function that kind of undoes whatever k did?
Is minus 2?
And minus 2. Makes sense? If I start with something, and then I add 2, the way to undo that is to subtract 2, and now I'm back where I started. Right? And, we could actually have Disco kind of check this for us. We could say, like, for all z of type z, kn of k of z equals z, and k of kn. Right, so either way, if I do like k and then k inverse, or if I do k inverse and then k, either way I always get back to where I started. So again, Disco can't prove this for us, but it can try it on a bunch of examples, and it does okay, right? It tried a bunch of examples, they all worked, so. Here's another function. I'm going to call this, I'm running out of names, so I mean, I'm not running out of names, there's plenty of names. Just running out of one-letter names, that's the problem. Pizza is going to be defined as 3x plus 2. So my question is this function invertible? Okay, what does it mean to be invertible? It means two things, right? It has to be 1-to-1, and it has to be onto. So, how about 1-to-1? What do y'all think? Is it possible to put in two different values for x, and then that give me the same thing out? No, that's not possible, right? So this is 1-to-1. Is it onto? Adam, say no? Why not?
Yeah, because that, like you say, you put in like 0, you get 2, and well, it's for all possible integers, right? So it's necessarily going to get computed.
Right. Yeah, so right, I'm always going to get something that's 2 more than a multiple of 3. So anything that's not 2 more than a multiple of 3, I can't get as output, right? So for example, it is not possible to get 1 as the output of this function. So not I will have another one. I will call this like. So Q, I don't know if we've used Q in Disco before, but I mentioned it before when we were talking about sets. Q is the set of rational numbers. So it includes positive and negative. It includes the integers, like 3 is in there, but also 2/3, for example. So like, 2/3. Maybe 2/3, right? If I ask for the type of that, it says, that's Q. So, I don't know if we talked about this before, right? Disco does not, so unlike, if you know some other programming languages, probably they have some kind of floating point type that's like, decimals. Disco doesn't have that at all, because those are terrible, and we don't need them for doing discrete math. But Disco does have built-in fractions, and it'll do, if you type in 2/3, or whatever, it's not going to say 0.66666, it's just going to say 2/3. And so it'll do whatever fraction math you want. Okay, milkshake is going to be 1-to-1 for the same reason that pizza was 1-to-1. But is milkshake onto? Yeah, and of course, you look at this and you're like, well, they're defined the same way, right? But I already kind of warned you before that, like, the fact that they're defined the same way, well, it's also important the fact that this is Z to Z and this is Q to Q. So, given the fact that our domain and codomain is all rational numbers, is this onto? Yeah,
Probably, yeah.
probably yes.
Yeah, just because, it's used, we use fractions, and you could technically,
prove that it's onto, I could say, you know, let y be a rational number. And then we want to find some x, some rational number x, such that milkshake of x equals y. Right, that is, well, milkshake x is 3x plus 2 equals y. Can I solve that for x? Pretty simple algebra, right? Solving for x, x is y minus 2 divided by 3. And, right, if y was a rational number, then y minus 2 divided by 3 is also a rational number. Because, yeah, any rational number, if I subtract 2, still a rational number. If I divide by 3, I'm just like putting an extra 3 in the denominator or something, so it's still rational. So, indeed, and onto. So this function, milkshake, is invertible. And this is the inverse right here. Like, this is the function that does the inverse. Any questions? All right. Again, here, the next, so, reminder that module, whatever number module we're on now, three, is due today. So, hopefully, hopefully I will hear from everyone today, either to turn it in or to ask for an extension. Either one is fine. I know a few of you have already turned it in. And then your next module will be, it'll be posted soon. I haven't finished making it, but, yep. So, have a good weekend. I will see you all on Wednesday.